We will now figure out plane equations for a bunch of different conditions. For all these questions, you need to know that for a plane equation, you need the normal vector and a point that it passes. A point that passes, like say x1, y1, z1. And the equation that passes through point P and has the normal vector n is ax minus x1, b y minus y1, and plus c z minus z1 equal to 0. So that's basically the idea. You need to find the normal vector and you need a point. And in all of these questions, you do have at least one point given. So you can use these for P. And if you have more than one point, it doesn't matter which point you use, you will end up with the same answer at the end of the day. Just like how you get the same equation if you use the point slope form. So therefore, in all of these questions, you have to find the normal vector. That's the problem. So let's start with A. In A, you have 3 points, and you want a plane that passes through the 3 points, and you do that by figuring out the normal vector that's perpendicular to both of them. Okay. And how do you do that? Well, we use the fact that cross product u cross v is normal or perpendicular to both u and v. And that's actually a common strategy we are going to incorporate in many of these questions. Okay, I think A, B, C would be using these. Okay, all right. So we're going to call the first vector here as u and the second vector as v. And by that I mean I want the first vector to be the vector that connects the first two, and third so that'll be our u, and the vector that connects the first and the third would be considered as v. But that's not the only way. You could use first and last to be u and these two to be v. Again, whichever way you do, at the end of the day, the equations that you get will be equivalent. All right. But anyways, once you choose your points, then the vector connecting those two is always figured out by doing terminal minus initial, right? So that's 1, 0, negative 2 minus 1, 2, negative 1, which gives you 0, negative 2, negative 1. So that's your vector u. Vector b, v would be connecting these two, so 0, 2, 1 is my terminal point, minus 1, 2, negative 1 is our initial point, and then I get negative 1, 0, positive 2. Okay, and then I need to do the u cross v to get the normal vector, and you do that by doing I, j, and k, and then you get you put u, which is 0, negative 2, negative 1, and 0, no, negative 1, 0, and 2. And then you use the expansion, row expansion with the first row, so I times deleting the row and the column that contains I, you get this. And then the checkerboard of signs goes like plus, minus, plus, minus, plus, minus, plus, minus, plus. So for j, you need a minus. Then deleting the column and the row containing j gives you 0, negative 1, negative 1, 2. And then plus k, 0, negative 2, negative 1, 0. 0, negative 2, negative 1, and 0. Okay. And then you do AD minus BC for each of these to get the determinant of 2 by 2. So that gives you negative 4, negative 1, actually, yeah, negative 1, and then to negative 2. So in terms of coordinate notation, it'll be negative 4, 1, negative 2. That's our normal vector, and therefore the answer would be negative 4, x, we'll choose the first one, x minus 1, and then plus 1, y minus 2, and then plus negative 2, z minus negative 1. Okay, we can simplify this by multiplying things out. So you get negative 4x plus y minus 2z, and the numbers are 4 minus 2 minus 2. Oh, so it's 0, right? This is positive 1 times negative 2. There's negative 2, and positive 4. So this is equal to 0. So that's the answer. Some of you might have changed these two. In that case, you might have 4, negative 1, positive 2. That's another equivalent answer. So it's this the same thing as 4x minus y plus 2z equal to 0. So that's another possible answer. So that's either these two will be the answer. Okay, let me add that when you have 3 points, there's another way to figure out the equation for the plane by using the fact that the 3 vectors being collinear means if you have 3 vectors, that means u, v, w are coplanar. And you can use this in such a way. We still use the same u and v. So what was our u and v? It was 0, negative 2, negative 1. So for this one you can do 0, negative 2, negative 1. Is that right? Yeah. And then for v, negative 1, 0, 2. Negative 1, 0, 2. So negative 1, 0, 2. And then for the third one, you just say you put x, y, z as a point on the plane, and you do terminal minus initial to get x minus 1, y minus 2, z plus 1. And you set this equal to 0, and then if you expand this using row expansion or whatever, you would get the same equation, but you're probably going to see that this gives you the answer in a quicker way, just because you can expand using a row or a column that contains a 0. So that's another idea. But I just wanted to show you the first method because the other remaining cases can be solved in a similar way. Okay. So now we have 2 points and the x-axis, and you're supposed to have a plane that passes these 2 points, but it's also parallel to this. So if you have this direction vector and if you bring it up, you'll see that that direction vector can be thought as a vector inside that plane. So if you have a vector that starts here and ends there, and you have another vector in there, then you have 2 vectors hopefully pointing in different directions that's entirely in this plane. So that's good because now I can just take the cross product of these 2 vectors to get a normal vector. So that's our strategy. We're going to say u is terminal minus the initial 0, 1, negative 2 minus the initial, which gives you negative 3, negative 1, negative 2. And the x-axis, what's a vector that's in the x-axis? Well, it's the I vector, right? The I vector is the direction vector of the x-axis. So we just do the u cross I, which is I, j, k, negative 3, negative 1, negative 2, and 1, 0, 0. Okay. Now in this case, usually you expand in the first row, but I would say I want to expand in the third row because it'll be 1 times the determinant of that, right? So what does that tell us? That tells us that you have 1 times j, k, negative 1, negative 2, which gives you negative 2j plus k, or in coordinate notation it'll be 0, comma, negative 2, comma, positive 1. So I'm doing AD minus BC, right? Negative 2 times j is what I got here. Negative 1 times k is negative k, but you're subtracting BC, so that's why you get this. And once you get that, now we can just plug it into the plane equation. X minus 3 plus negative 2 y minus 2. I'm using this point, 3, 2, 0. Okay, 3, 2, 0. So 3, 2, 0. And therefore this is a 0. This is negative 2y plus 4 plus z equal to 0. And this is fine, or you can move the 2y and z to the other side and write it as 2y minus z equals to 4. So that's the answer. This would have been a perfectly fine answer too. Okay, part C. Now this time you're given another line other than x-axis, and I know what this direction vector is. This is over 1, so in the symmetric formula for lines, the denominators give you the direction vector as long as it's x, y, and z. If sometimes you might have a negative y, then it's destroy this. In that case, you really need to first change it into parametric form and then differentiate the resulting parametric form to find the direction vector. But I'm just taking a shortcut. So I'm claiming that this line has the direction vector 4, 1, negative 1. If you're not sure, try to change it to parametric form and differentiate. You will indeed see that this is the direction vector. Okay, now therefore it's the same story as before. We had negative 3, negative 1, negative 2, negative 3, negative 1, negative 2 as this vector connecting the 2 points, and what I need to do is to cross product this with 4, 1, negative 1, and that's going to give us our normal vector. Okay, which is I, negative 1, negative 2, 1, negative 1, and then minus j, negative 3, negative 2, 4, negative 1, plus k, negative 3, negative 1, 4, and 1, and that's 1, so that would be 3i, 3 and 8, so that's going to be 11, so minus 11j, negative 3 plus 4, positive 1, so it would be positive 1k. So that's going to be 3, negative 11, and 1. And now we just write down the equation 3x minus 3 minus 11y minus 2 plus 1 z minus 0 equal to 0. And I'm using 3, 2, 0 from here. It has to pass that. So it's 3x minus 9 minus 11y plus 22 plus z equal to 0. So 3x minus 11y plus z, that's 13 minus 13. Okay, so that's the answer for part C. Okay, now I need something that's perpendicular to this line. As I said, this has 4, 1, negative 1 as its direction vector, and since this has to be perpendicular to this, so part D is actually a really easy question because all you need to do is you need a normal vector, but the normal vector is already given because we're given that this line is perpendicular. So our normal vector is 4, 1, negative 1. It has to pass through 3, 2, 0. So the answer is 4 times x minus 3 plus 1 times y minus 1 plus negative 1 times z minus 0. So that's the answer, and if you simplify, you're going to get this, and then let's see, negative 1 minus 12 equals to 13 should be the answer. Okay, what about E? Now I need something that passes through this, and it contains this line. So for this, one way to do this is just pick 2 points from here. You just plug in t equals to 0 and t equals to 1, and then you get 2 points on this line, and that will be enough, because if you're given 3 points, you can solve it just like part A. So that's one strategy. Another strategy is to just find 1 point in here, connect this one with that one, and make a vector, and then use this direction vector to be another vector and do the cross product. Okay, so let me show you briefly how that one works. So if t is equal to 0, we know that you get 1 comma, if t is 0, you get 1 comma negative 1 comma 3 is a point on the line. Point on the line, which is inside the plane. Okay, so let's define u as terminal point being this point, initial point being our 1, 3, negative 1, and the resulting thing is you get 0, negative 4, positive 4 as our u. Okay, and then you do u cross the direction vector of this. If you differentiate this, you get 3, 5, negative 1. That's the derivative, right? So write that derivative, do the cross product, which is I, j, k of 0, negative 4, 4, and 3, 5, negative 1, and that's I, negative 4, 4, 5, negative 1, minus j, 0, 4, 3, negative 1, plus k, 0, negative 4, 3, 5. Okay, and then what is that? That's going to be 4 minus 20, that's negative 16i, 0 minus 12, so that is plus 12j, and then 0 plus 12k. Okay, and therefore if you have negative 16, let me see, negative 16, 12, 12, okay, negative 16, 12, 12. Okay, so negative 16, 12, 12 as the normal vector, and it has to pass through this point, so we have negative 16 x minus 1 plus 12 y minus 3 plus 12 z minus negative 1 equals to 0. Now I would divide by negative 4 because they are all divisible by negative 4, so this will be 4x minus 1 plus 3y, actually minus 3, y minus 3 minus 3, z plus 1, and if we simplify, this will be 4x minus 3y minus 3z, negative 4 plus 3, negative 1, negative 4, so this is going to be 4. So that's the answer to E. Now I still want to show you yet another method which you may have not seen. It is totally foreign in some way. What you want to do is you have x equals to 3t plus 1, y equals to 5t minus 1, z equals to 3 minus t. So you can change this to symmetric form as x minus 1 over 3, y plus 1 over 5, and z minus 3 over negative 1. That's all equal to t, right? And you want to think of this line being in the intersection of this plane and this plane. Okay, so what is this plane? let's cross multiply and see what we get. 5x minus 5, 3y plus 3. So 5x minus 3y minus 8 equal to 0. That's this plane. That's the first plane. This plane here is cross multiplying negative y minus 1 is 5z minus 15. Move everything to the other side, you get 0 equals to 5z plus y minus 14. Okay, and then think about this. Anything that's on here, because it's in the intersection of these two planes, it's going to satisfy both equations. Which means if I decide to write another plane equation, so I'm multiplying by some number a to the second one, this is still going to be a plane. If let's say a is 1, for example, then if you simplify, it's going to give me another plane equation. But because these three numbers satisfy both being 0, 0 and 0, it will still give you 0, which means this line in question is again on this line also. And then all you want is 1, 3, negative 1 to be on this plane. So see, this is some arbitrary line that passes through this line. I'm sorry, this is some arbitrary plane that contains this line, and we have this some arbitrary value. And what I'm saying is that a has to be some fixed value if I want it to pass through 1, 3, negative 1. So let's do that. 1 plugged into 5 gives you 5. 3 plugged into 3, that's not negative 9, plus a. And then z, you plug in negative 1, so negative 5. Y, you plug in 3, minus 14 equal to 0. That's negative 12, right? And then plus negative 16a. So that gives you that a must be negative 3/4. So you plug that in here, and the resulting equation is 5x minus 3y minus 8 minus 3 over 4, 5z plus y minus 14. And the amazing thing is, if you multiply by 4 and simplify this, you will eventually find that you end up with the same equation as this after simplification. So that's just another approach. It might give you the answer more quickly than this one, but whichever method you're more comfortable with, you should use that.